I replied it, Mr. Nilesh, about your mail. Check the mail. I replied it. Have you received, Mr. Nilesh? So you just do the calculation. CDF you want to do. In the CDF, nothing is special. No, there is no need to remember the table values. It is provided in the question. Okay, it should be either table is provided, required table values are provided to you. So there is no need to remember table values. Okay, and the CDF is what? We can say the CDF is denoted by the fx, and it is what? Probability when x is less than equal to small x. So in the discrete case, we are taking the summation up to the x point, and we are just adding it, the mass function. And in the discrete case, and in the continuous case, we are integrating from x is equal to minus infinity to x, or t is equal to minus infinity to infinity, and ft dt. Okay, so that is the part, the CDF. So you just do the addition or integration for the finding all probabilities up to that point. Okay, so welcome you in the context session 11, and we were doing the joint distribution. So we have done the joint distribution at bivariate discrete case, bivariate continuous case. Now we are extending that in the multivariate random variables, means what? N-dimensional variable. So that is the same as we have already done, that we are just having the discrete case or continuous case. Accordingly, we can just do the same. So you can see here, if x1, x2, xk are the random variables, so we can say this is the ordered set with k elements, x1, x2, xk, a k-dimensional continuous random variable. So here we are talking about the continuous random variable. So joint density function can be as defined as they should be greater than equal to 0, and integration k times that it is equal to the probability of this density function, and this probability belongs to that region R in the domain of specifically the joint density function f. Okay, so as we have done in the two-dimensional, same thing we can do for the n-dimensional or k-dimensional. Okay, so there is nothing is specifically in this one. So the marginal for xi is also can be written as, f of xi, and it is integrating to k minus 1 times dx1 to up to dxk, but we are not doing the integration with respect to xi here. Okay, so for example, if we are talking about, so if we have the three-dimensional or four-dimensional, if we are just talking about the four-dimensional, so we are saying fx1 of x1, that will be what? We are doing the three-time dimensional, so it is x2, x3, x4, all range of x3, x4, x4, and here we are taking the joint density function for x1, x2, x3, x4, and now we are just integrating with x4, x3, and x2. Okay, so this is a four-dimensional, and we are finding the marginal with x1 with respect to x1. Similarly, you can find out for the x2 and then x3 here. Got it? So random variable x1, x2, xn are called independent if the joint density function, joint distribution is equal to the product of the marginal density function. So same concept we are doing, but most of the time in the real life examination, we are just using the two. So that's why specifically we have done the bivariate, but the same type of extension we can do if we have the three-dimensional, four-dimensional, five-dimensional, and so on. Nothing a change which we have already done earlier. Okay. Similarly, the expectation for the n-dimensional. So what we are taking expectation of any function can be written in the discrete case summation up to the that n-dimensional, and here the function multiplied by joint density function here. Okay, and in the continuous case, what is the change? We are just taking the integration k times, and then our function, and then our joint density function, and different integrating with respect to x1, with respect to x2, with respect to xk respectively. Got it? Any query? Yes, please reply me back. Am I audible? Okay, fine. So it's clear now. Any query in this case? So we are just doing the same thing which we have done earlier, but in the n-dimensional form. So no new concept, only the same concept which we are extending it. Okay. Similarly, the variance of two variable. So we are using variance of x plus y. So variance of x plus y can be written as variance of x plus variance of y plus 2 times of k variance of x comma y here. Okay, and similarly variance of x minus y is variance of x plus. So be careful in this case, it should be plus only, variance of y and minus of 2 covariance of xy. Okay, so when they are not independent, when the two random variables x and y are not independent, so we are just talking about the covariance of xy, and covariance of xy is what, if we are just saying here in a very proper manner, so it is expected value of xy minus expected value of x into expected value of y. This is the formula to calculate the covariance here. Okay, and that covariance is just showing the linear relationship between the x and y here. When we are just taking more general, so variance of summation of ai xi can be written as summation of ai. 1 second, 1 second, just give me 1 second. Oh, sorry, there's some disturbance actually. Am I audible? Okay, fine. So at the time it will become here 2 times of covariance summation of ai aj covariance of xi xj. So if we are writing for example, if we are just talking about the variance, what is going on, variance of, let us suppose we are taking here a1 x1 plus a2 x2 plus a3 x3. For example, we are doing like this one. So what we are taking, a1 is square variance of x1 plus a2 square variance of x2 plus a3 square variance of x3. Now we are just taking 2 times of a1 a2 covariance of x1 x2. Okay, and plus 2 times of a1 a3 then covariance of x1 comma x3, then plus 2 times of A2 A3 covariance of x2 x3. So this is the general, we can say that particular form of this general formula here. Okay, so it is given in the summation form, but we are just open it for the three variables, and a1 a2 a sorry, so these a1 a2 a3 are the constants. Okay, so now we are just taking about the if independent and identical distributed random variables. So independent we have done, identically also we have done. Independent means what? Covariance is equal to 0 and the joint distribution is equal to the product of the marginal distribution. Okay, that we have done. Identical means what? They are having the same type of distribution, they are coming from the same sample space. Okay, so let S1, Xk, Xk are the independent and each has the same marginal distribution. So we say X1, X2, Xk are independent and identical distributed, and the word is IID here. Okay, so that we are just using this IID term, that is they are independent and identical distributed random variables because their marginal density function is coming the same for each variable. Okay, so that we will use in the statistics part, and before doing the statistics part we are doing the moment generating function. I'm sorry. So moment generating function is what? So if you remember, we have done the expected value of hx can be written as what? In the discrete case, summation for all x, we are multiplied hx with the density function here. Okay, and we are taking the summation that you have done now. So we are just saying here first part that hx is equal to, we are saying x. So at the time that you are have calculated the expected value of x for every x fx, correct? Now we are just saying here, this is hx, this function will become here e to the power tx. Okay, so expected value of e to the power tx will become like summation for every x e to the power tx into fx. Correct. So this is known as the moment generating function. Okay, so moment generating function is denoted by mxt and it is expected value of e to the power xt here. Okay, and by definition this is the formula, and when we are just going for the continuous case, this is for discrete case, and for continuous case that x e to the power tx fx dx. So we are doing the integration for it. Okay, now we are just doing this moment generating function for each distribution. So firstly, we are just defining the binomial distribution. So what it is required, that either discrete or continuous, and then we are using the joint density function. So here binomial distribution, if you remember, if you can recall, so this is the this is a density function, the probability density function of a binomially distributed random variable, that LCX p to the power x 1 minus p to the power n minus x for x is equal to 0 1 to n here. Okay, so in that case we have to prove that the moment generating function is this. How we can do it? We can just use the direct formula. So mxt is equal to what? We are just taking e to the power tx, and this is what our fx. Correct. Now this e to the power tx we are just writing here with the p. So e to the power p x 1 minus p to the power n minus x, and by using the binomial theorem, because from that we can find out. So this is the formula for the binomial addition. Okay, so this is known as the p e to the power t, this is 1, and 1 minus p to the power n whole. Okay, because x is equal to 0 to n. So by using the binomial theorem, we can find out this is the moment generating function. So what is the moment generating function? P to the power t plus 1 minus p whole power n here. Okay, this is the moment generating function for the binomially distributed random variable. Can you anyone can tell me what is the expected value of x in the binomial distribution? If x follows the binomial distribution with parameter n and p, so what is the expected value of x and what is the variance of x? You can recall because in the next class, next week you have the examination. Correct, Mr. Venkata. So it is NP and this is NPQ. Or we can also write it is NP1 minus P. है ना? So from that we can also find out in the summary sheet. If you remember, I also discussed with the moment generating function and I told you that we will discuss later on. So here it is what? P to the power T plus Q to the power N here. Okay. That is the moment generating function here. We didn't element NCX. NCX is already be there. NCX is already be there. That is by the binomial theorem. Then when we are using NCX, that P to the power, if we are just saying binomial theorem, so NCX, if we are taking summation, x is equal to 0 to n, a to the power x and b to the power n minus x. So at the time, this formula will become a to the power b, a plus b to the power n. Got it? So this is known as the binomial theorem, basically. Okay. So from that, we are getting this part here, binomial theorem. Second is, so the word is coming, why we are saying it is moment generating function, because it generates a different movements. So first movement, you know very well, it is the first movement and this is the second movement about the mean. This is the first moment about the origin. Okay, so what we are saying here, that moment generating function, that is mxt, generates the moments about origin. So what we will do, we differentiate it with respect to t, and after that put t is equal to 0. Okay, so first differentiation, then first movement. First movement okay, and that first movement, oh, this first movement is what? Expected value of x. Correct. When we differentiate it twice, mxt, okay, and then put t is equal to 0. So this is given the second movement. And this second movement is what? Expected value of x square. Correct. So now in the binomial distribution, this is what? Expected value of the kth movement we can find out. We differentiate it is the that m of this k, this one. This is the kth differentiation actually. Okay. So it is given in the superscript k, in the bracket, it means kth time differentiation. Got it? So that will give the expected value of x power k. That is the kth movement about origin here. Clear? So now if we are saying here x follows the binomial distribution with parameter n and p, and we know the moment generating function is what? That is p to the power t plus q to the power n. Correct? Now we differentiate it with respect to t. It is very easy. So it will become n, then p e to the power t plus q to the power n minus 1 into p. And we have to do the with respect to t. So p e to the power t here. Now we put t is equal to 0. mxt, put t is equal to 0. So what is coming here? If we put t is equal to 0, so it will become n p e to the power 0 plus q to the power n minus 1 into p e to the power 0. Correct? Now you just simplify it. So here it has become n. It has become p plus q to the power n minus 1 into p e to the power 0 is 1. Now what is this? P plus q is what? Do you remember what is the value of q? Q is what? 1 minus p. Okay, so p plus q is 1, 1. So it has become np 1 to the power n minus 1. So this is np. So this is the another formula to calculate the expected value of x by using the moment generating function. Correct? Now we can differentiate it again. Of mxt. So when we are just to differentiate it, it will become here n minus 1 n p square e to the power 2t p e to the power t plus q to the power n minus 2. Correct? This is the first term. Second term is what? N p e to the power t, p to the power t plus q to the power n minus 1. Correct? Now we are putting t is equal to 0 in this case. So it will become here n minus 1. Just a minute. Got it? Any query? So when we just substitute, here t is equal to 0 in this one, so it will become here n minus 1 n p square e to the power 0 p e to the power 0 plus q to the power n minus 2 plus n p e to the power 0 plus p e to the power 0 plus q to the power n minus 1. Got it? So now what is this? This is 1 to the power n minus 2. This is 1 to the power n minus 1. So what is remaining here? N minus 1 of p square plus np. Okay. Now we can find out the variance. Variance of x is what? Expected value of x square minus expected value of x whole square. Everything is available here. N minus 1 p square plus np minus n square p square. So when we are open, is this n square p square? Open it. N square p square minus n p square plus np minus n square p square. So these are cancel out. Now np is common. So np is common, 1 minus p is remaining. So it is npq. Got it? Any query in this one? Are you getting? Please reply me back. Are you getting these points? So this is the use of the movement generating function. Then without using the complete formula, that summation for all x fx, that is become a little bit lengthy. So what we are doing, we are just calculating these moments or these parameters, that is expected value of x, movement, the variance of x, by using the movement generating function. Okay. Next is for the Poisson distribution. So if you remember, this is the probability density function for the Poisson distribution for x is equal to 0, 1 to infinity. Now we can find out their movement generating function. So it is given that show that, there is no need to define it, show that. Okay. So what we are saying, the Poisson distribution, the movement generating function is what? Summation for all x. Okay. And then e to the power, e to the power tx and lambda to the power x e to the power minus lambda upon x factorial. ठीक है? So when we are just simplified, x is equal to 0 to infinite. When we are just simplify it, so it will become like e to the power lambda and e to the power t minus 1. Okay? For every value of t. So that will become the movement generating function for Poisson distribution. And when we differentiate it, d by dt of e to the power lambda into e to the power t minus 1, put t is equal to 0. So that differentiation is what? That is become here lambda e to the power t minus, oh, e to the power. Okay, we are just taking the differentiation of this expectation value and then multiplied by e to the power t into e to the power lambda. Okay. Put t is equal to 0. So that is become here 1, 1 minus, just a minute. Just a minute. So we are taking lambda e to the power t as this and e to the power lambda e to the power t minus 1. This is one. Okay. Put t is equal to 0. So here it will become lambda e to the power 0 e to the power lambda e to the power 0 minus 1. Okay. So e to the power 1 minus 1 is 0. So it will become here lambda into 1 into 1. So it is equal to the lambda. Now you got it? Any query in this one? Okay. Similarly, we can find out the expected value of x squared, that is the double differentiation, and put t is equal to 0. So it has become lambda plus lambda square. So variance of x is equal to, here you can say lambda plus lambda square minus lambda square. So this is cancelled out. This is also lambda. The variance of x is equal to lambda. Expected value of x is also lambda. Clear? Any doubt in this one? Now, similarly, we can do the for moment generating function for the normal distribution. So, binomial distribution, Poisson distribution, and normal distribution. We are not doing for more. So, this is the density function, if you remember. So, moment generating function is given by this one. Okay, and this is the continuous case. So, what we are doing, mxt is equal to integration for x is equal to minus infinite to infinite to the power tx and then fx. into dx. So e to the power tx fx dx. Correct? We solve it, this integration. The solution of the integration is not required at all. Okay. It's not required at all. That's why I'm not solving it. I'm just telling you that concept, that how we can calculate and how we can obtain the moment generating function here. Okay. So this value is coming e to the power mu t plus half t square sigma square here. Now we differentiate it. So it will become first differentiation. In the previous slide, in this one, we are differentiating this one now. We are differentiating this one, e to the power lambda e to the power t minus 1. So if we are just open it now, I'm doing here e to the power lambda e to the power t minus lambda. है ना? That is this concept. So we differentiate it with respect to t. So e to the power minus lambda is coming constant. So that is become 0. So that's why we are just taking lambda e to the power t, this part, and e to the power lambda e to the power t minus same lambda. Got it, Mr. Mahendra? Similarly, in this case, we differentiate it with respect to t e to the power mu t plus half e to the power, this is the exponential term, and how we can just take with respect to t. So constant is coming mu, and here it is also t sigma square. Okay, because that is coming 2t, 2 is cancel out to t sigma square. And when we are putting t is equal to 0, this term will become 0 and this term will become also 1. So that answer is mu here. Okay, similarly we differentiate it twice and put t is equal to 0. So if we are putting t is equal to 0, that will become 1. So this is become here mu square plus sigma square. So that is expected value of x square is equal to mu square plus sigma square, and variance of x is equal to mu square plus sigma square minus mu square. So mu square cancel out, that is sigma square. Okay. Now one theorem, again the proof is not in your syllabus. So we can find out if z is equal to x plus y. So the moment generating function of z can be written as a product of the moment generating function of x and comma y, provided that their moment generating function should exist. Okay. So the product of the moment generating function of x comma y can be written as the moment generating function of z. So from that we can say if they are independent normal random variables. So if they are normal distributed, but they are independent also x, y. And x has the mean mu x, variance sigma x square, y has a mean mu y and variance sigma y square. So the use moment generating function to find out that x plus y. Okay, that is the z is equal to x plus y, or we can write not z, we are writing t is equal to x plus y. So x and y follows the normal distribution, they are independent also, so t also follows the normal distribution. How we can prove it? By the moment generating function, and what is the parameter that we have to find out. Okay, so in that one we are saying this is the mean is mu x plus mu y and variance is become sigma x square plus sigma y square. Okay, so how we can do it? So mxt is equal to e to the power mu xt plus half t square sigma x square. Okay, by the formula which we have done, the moment generating function of a normal distributed random variable. Similarly, we can write it here for y. M by t is e to the power mu y, mu t y, and half t square sigma y square. So this is the form, you can say the power of exponential. Okay. Now we multiplied it. Okay. So it will become e to the power t mu x plus mu y, and half of t square sigma x square plus sigma x y square. So it is the same moment generating function as the normally distributed random variable have. Correct? So what we can conclude, that this variable, which is the moment generating function of mxt myt, also follows the normal distribution with mean is equal to mu x comma mu y plus mu y, and variance is sigma x squared plus sigma y squared. Okay, that is the use of the moment generating function. Basically, first is to calculate easily the movements, different movements, and also if there are two random variables, they are adding their subtraction. Okay, so we can also find out their distribution. Okay, so another variable we are finding t, which is the addition of x plus y, where x and y are the normally distributed random variable and independent. Then we can also find out the t also follows the normal distribution, but the parameter is what? The addition of the both mean and addition of both variance. Okay, are you getting my point here? This is the second use of the moment generating function. That's why in probability theory, moment generating function have a very specific role. Any doubt, any query in this one? Okay, thank you. Thank you so much. So now we are just moving to the statistics part, random sample from a finite population. Okay. What type of question? For example, T is given. For example, T is given x plus y. I'm saying x follows, I have given a one example that x and y follows the normal distribution. Okay, what is the distribution of T? Okay, and there is no need to remember the formula because that part is not coming in the EC2, that is a closed book. So that part will come in the EC3 only, and that is the open book examination. So there is no need to remember the formula of the moment generating function as well. Okay, so don't think that we have to remember so many formulas. Second thing, question is what that I'm saying. For example, x and y follows the Poisson distribution. What is the distribution of the t? X and y follows the binomial distribution. What is the distribution of t, and so on? One type of question we have already done for normal distribution. Okay, so now we are taking a random sample from a finite population, a simple random sample of size n from finite population of size n. Okay, not last class, last to last class. Do you remember? The joint distribution will not come in the your EC2. In the last class, we have discussed about the joint distribution. So that is not coming in the part of the EC2. Today's class also will not come in the EC2. Okay. So this part, whichever we are doing here, that is the part of the EC3. Okay. Now we are just What is the last distribution? That is the before section 5.10. 5.10 is what? Joint. So before it. Yes, correct. Before joint distribution, it is up to the exponential distribution. We have done the exponential distribution. Mr. Rahul, you are correct that we can explain some briefly, but we don't have the some time actually. You can see, according to the handout, we are going in a very slow pace and we are not able to cover the syllabus at the end because we have the limited time to cover up the syllabus also, no? So you have the recordings, you just go through the recordings. Any doubt you can mail me. Mr. Nilesh also mailed me. They dropped a one mail and I tried to reply it. Okay. So if we are taking the revision, it's very difficult for me to cover up the syllabus actually. And we are also I also don't have so much time actually. I have to cover up the syllabus. So it's very difficult for me to just take the revision part also. Okay. Because now we are, the course name is probability and statistics. So up to chapter 11, we are doing the probability theory only. We have to just cover up the statistics part also. Last to last class, Miss. Okay. So I already told in the first class when we just mentioned that we have like for this one a complete sample space. So that is known as the population, correct? And in that one we are just collecting a some small part. So that is known as the sample here. So in the first class, I already explained what is the population and what is the sample. Means what? There are 400 students involved in this, enrolled in this particular course. But right now, how many students are attending the class? 46. So I am just asking to you that, okay, it's clear, any doubt, any query, and based on your reply only, I just do the, or I just inferred something about the population that, okay, if all 400 students are thinking and they just having the same perception as you all 46 have. Okay, so that is the 46 students who are attending the classes. That is the sample, and based on that sample only, I inferred something about the population that, okay, these parts are already covered. So how they are attending the classes, how they just cover up this course, we don't know. But we are just trying that, okay, they can see that recording and then they can just do the practice for the examination preparation. Correct. So that is the n sample here, n size, population size, and we are collecting the some sample of small n. Okay, in such a way that each possible sample of size n has the same probability, because all students are same. So for me, that is all, they are equally likely. So it means they have the same probability of being selected. Got it? So I can't say right now the probability is very less, but we can't say like right now. Maybe some students are not able to attend the class. Okay, so he's not attending the class, but he's just doing some work, and this part properly they prepared it, and then in the examination they got the good marks. So the probability of coming good marks, if we are saying probability of coming good marks, that is same for each student. Okay, all 400 students, I can say that probability of coming good marks, this is same for all students. They are not saying that this is more for some students and this is less for the some students. We can't say like this one. It depends upon the that how all students are preparing it. Okay. So this is a sample we are talking about, and in this sample we are doing some calculation. So that calculation is known as the sample mean and sample variance. Okay, so x1, x2, xn are the we have done already identical and independent distribution. Independent means what? You have done in the joint distribution is equal to product of the marginal, and identical means having the same type of distribution, same property. Okay, so let mu is equal to expected value of xi, then variance is equal to xi sigma square. Then we define the sample mean is what? It is denoted by the expected value xi and this. Okay, n means what is the sample size here, and that is equal to what? Summation of xi, I is equal to 1 to n upon n. So that part you know very well, the sample mean. So earlier, as I told you, that we have done the sample mean only, but in the probability theory, we are saying this is the population mean. Okay, you have calculated this one by the moment generating function by definition. That is known as the first moment, and that is what basically a population mean. Okay, so now we have the two parts, population and sample, and both having the mean, and both mean values are different here. Okay, so we are just saying here that expected value of x is known as the population mean, and x bar is denoted by the, it is denote the sample mean. Correct. Similarly, standard deviation and the variance Sn square. So you remember that we are just using the variance of x is like this one. We are denoting it by this one. Now we are just saying that the sample, we are taking the sample of size n. So the variance is coming by this formula. That is what? Summation I is equal to 1 to n xi minus x bar whole square divided by n minus 1. Okay, now the second thing is sample. Sample is again a random variable. We are taking the different sample and in the population of the same size n. Okay, so that is also be a random variable. So x bar is also be a random variable, and its mean is what? Mu. And variance of x bar is sigma square by n. And expected value of s square is equal to sigma square. Got it? Now we are just doing a one example here. After example, we will just take a break. So we are just saying here the sample, the population. There are 5 elements in the population, and their values grade is 3, 6, 9, 12, and 15. Correct? 5 population size. Now we are taking the different possible samples. So of size 3. Small n is equal to, so capital N is equal to capital N is equal to 5, and small n is equal to 3. So from this 5 we are just selecting the 3 values randomly, and there are all possible 10 options. Correct. So we are just saying here 3, 6, 9, 3, 6, 12, 3, 6, 15, 3, 9, 12, 3, 9, 15. So we are trying to find out all possible combination. So this is one a sample of size 3 from the population of size n, capital N. A capital N is equal to 5. Correct? So what is the sample mean is 6 here. But we change the sample, and this is the sample of size 3 only, but this is the different samples, different values we are collecting from the population, and its mean is 7 and its mean is 8 and so on. So that's why we are taking the sample mean is also a random variable, that which sample we are collecting out of this 10. Okay, so this is this one, and expected value, that's why I'm saying x bar is also be a random variable, and whose mean can be written as the mean of the population. Expected value of x bar is equal to mu. Expected value of x is not equal to the x bar. है ना? X bar is the sample mean and expected value of x is equal to population mean. Correct? Are you getting my point here? The sample, how we are collecting the sample from a one population. So we are taking a very small population and then we are just taking here its sample. So different samples are coming and we can find out their x bar, and x bar is also become a random variable because the sample which we are collecting, that is also a random. Okay, so their mean we can calculate. You can find out the mean of this x bar also, and the mean of this is equal to same. Okay, how we are getting this one? So because this is 10 times, so 6 is coming. Oh, sorry. So 6 is coming once, so it is 0.1, 1 by 10. 7 is coming also 1, so it is 0.1. 8 is coming 2 times, so 2 divided by 10. And 9 by 2. Are you getting my point here? Am I audible? Are the slides visible? Okay, fine. Thank you. Visible, correct. Okay, so we can find out their expected value. How we can find out the expected value of x bar? This is the random variable x bar. So it is equal to the 6 multiplied by 0.1 plus 7 multiplied by 0.1 plus 8 multiplied by 0.2 plus 9 multiplied by 0.2, then 10 multiplied by 0.2 plus 11 multiplied by 0.1 plus 12 multiplied by 0.1. And that is equal to the same as we have done this part. Okay. Thus, so expected value of x bar is coming 9. And variance of x bar is equal to 3. Yes, this is the sampling distribution. Okay. So population mean is equal to 9 here, and where population variance is equal to 18. So expected value of x bar is equal to mu, and variance of x bar is equal to sigma square by n. And this term is coming because it's a finite table, finite population. Got it? So just go through it. I'm just taking a break, and today I'm taking a bigger break actually for 15 minutes. Okay, just go through it, the sampling distribution I have done. I'm just opening the slide and you can just go through it. Just give me 1 minute only. Okay, screen not visible. Okay, just give me 1 second. That's the thing actually I'm trying to share. Stop sharing. I'm trying to connect it. Actually, there is some technical issue that I'm not able to. There is some connectivity issue. That's why it's not visible. I'm just trying to connect it. Just give me 1 second only. Just give me 1 second only. Up to the exponential distribution. I don't know. There is some technical issue. Just give me 1 second only. It's wasting our time. The technical issue that I am not able to connect this. I think this time it is connected. I'm sharing the screen again. Now the screen visible. Is the screen visible? Please check. Screen is not visible till now. Okay, fine. So you just go through this screen and I'm just taking a break. Okay, you also take the break for the tea or coffee. Okay. Am I audible? Okay. Actually, after 15 minutes, there is some technical issue. So I tried to sort out it. I believe it's sort out. Slides are visible now? Okay. Okay. Mr. Mahesh, EC2 examination course for the EC2 examination is up to the exponential distribution. This part is not in the not the syllabus of the EC2, which we are doing. Yes, Mr. Rohit. Before 5.10, not 5.1. Before 5.10 means 5.9, but 5.9 actually this is the section which we are not covering. Some other distributions are there, which is not in your syllabus basically, na? So that's why I'm not mentioning it's 5 up to 5.9. It's 5.10 up to the exponential distribution. Okay. So when our population is finite, capital N, so we are using this correction of finite one, that is capital N minus N, and is upon capital N minus 1. And otherwise it is sigma square by N. When population is infinite, so we are just saying here variance of x bar is become only sigma square upon N. It is because of the finite population, that's why this one. Okay, we have to repeat it again. So what we are doing, okay, I left it here because I believe. So this is the sample population. There are 5 students. There are 3 type of grades. Okay. Now we are selecting some samples. As I told you, this is a population. So we are taking the different population samples. So there are several samples of same size we can collect. So we are taking small n is equal to 3. This sample size is 3, and 10 possible combinations we are getting here. Okay. Now from that we can also find out the px by using that. Okay, this is first one time, this is 2 time, this is 2 time, this is 2 time, this is 1 and 1 time. So we can find out the probability of x. So we are saying the x bar is the sample mean. So the values are 369. The sample mean is what? 6. 3 plus 6 plus 9 divided by 3. So sample mean is also be the variable that is coming from 6, 7, 8, 9, 10, 11, 12. Okay, and this x bar, the sample is also variable. Its mean is also a variable, random variable, and its mean. So what we are saying here, that is mean of a sample mean. Mean of a sample mean is equal to the population mean. So we are just taking the formula here. So by using this concept, we have just showed you that expected value of x bar is 9 and variance of x bar is equal to 3. But we can calculate it here that population mean is equal to 9 and variance is sigma square by 18. So we can find out the formula as expected value of x bar is this mu, same, and variance of x bar is this one. Okay, and this is a finite population because this and capital N is equal to 5. That's why we are using this formula. If population is infinite, that we are using variance of x bar is sigma square by N. Now you got it? Okay, Mr. Vineet? Px is what? Px is what? Is we are just saying this one. If you are going back, 6 is coming one time. Total is 10. 10 possible combinations. So 6 is coming 1, so 1 by 10. So it is 0.1. 7 is coming 1, so 1 by 10. 8 is coming twice, so 2 by 10, and so on. Okay. So random sample is known as, it's a constitute of random sample of size, and that size is also very important, from the infinite population. So generally we are considered an infinite population, not the finite population as we have done. Okay. So we are taking the finite population, infinite population, and these are the independent, and these are identically distributed. So we are just using the word IID now, independent and identically distributed. And what is the means of the identical distribution? That they are coming from the same population. Okay, so we are saying xi are the IID, then we are saying it is a forming a random sample. Okay, so we are just taking one more example here. Suppose there are 2500 managers in a company. Okay, we would like to develop a profile of managers with their mean annual salary and proportion of managers who complete company's management training program. So there is a company program actually. So there is a, what is their salary, annual salary, and what is that database we are making. Suppose a population mean salary is given here. Mu is equal to $51800. Okay, and population standard deviation is $4,000. Are the slides visible to all of you? Okay, screen is not changing. Slides not moving. Okay. Now? Okay, now it's moved. So I think there's some internet connection problem, maybe. Hannah? Just give me a 1 second only. I just start the charging of the tab also. Just give me 1 second only. Okay, try to rejoin. So slides is visible now. So as I told you, 2,500 managers in a company, and they were just like a profile of managers. So they just make up with the mean annual salary and the proportion of the managers who are just completed their training program actually. So the population mean of salary is what? $51,800, and population standard deviation is what? $4,000. But 1,500 managers have already completed the training program. So population proportion is what? P is equal to 0. Okay. The information is given like this. Now audio is coming. I'm trying to rejoin it. No, audio is okay. I'm trying to rejoin the tab also. There is some connectivity problem, I think. Now slides are visible. Are the slides visible? Okay, fine. Thank you. So what the thing is, we have the 1500 or 2500 managers. Okay, and we have sent find out 1500 managers are completed their training. So P is equal to 0.6. Okay, the probability is of success is what? 0.6 here. Now we are just collecting the 30 managers. So this is the population. But small n is equal to 30. So that is 30 managers are there. Okay, we selected, and then we just check their what is their salary and what is their they completed or they completed their project on or their training or not. Okay, so first one, second one, third one, and so on. So you can see here, fifth one is not done their training. Similarly, this one, this one, this one, and so on. So 30 managers we have selected randomly, and then we calculate their value. Okay, so from that we can find out that x bar is equal to, because this is sample, so in sample that we are calculating the x bar is $51,814. Okay, and his sample standard deviation, you have done the formula, sample standard deviation is $3 comma 348. So the probability of success is 0.63. है ना? Actually, the population is having the $51,800, and sigma is equal to the standard deviation is equal to $4,000, and probability of success is 0.6. That is the difference between the actual one, whatever the actual in the population, but we are collecting for the 30 managers, and that we are collecting these points here. So this is the meaning of the sample space. We are taking the sampling from the population, and we inferred something about the population. Okay, now it's clear to all of you. Now we collect the 0.63. You can see that 19 managers at completed their training out of 30. So 19 by 30 is 0.63. Okay, and why we are taking the P bar? Because this is from the sample, so we can differentiate between, we can distinguish between the population parameter and the sample parameter, basically. Got it, Mr. Mahinder? So now we are just taking the another sample of 30 managers. This is the one sample we have taken. Now we just take the another sample, and we found the mean, sample mean is this. Sample proportion is 0.70. And now we have done so many times, 500 times we have done. Okay, 30 managers we are taking. all times. They may be same, they may be different. Okay, so at the time 500 times we have done, so that means what, we are just randomly choosing. Okay, and from that, that sample proportion is also different for each one, so it is a random variable. Sample mean is different from each one, so it is also be a random variable. Okay, so what is the some remarks over the random sample? Basically, in practice, small n upon capital N is less than equal to 0.05. So we can consider it's a random sample. Means what? Capital N, you can say here 2500 managers are also considered as finite. But here you can say n upon 25 n. Okay, that is 30 upon 2500 है ना, and that is always be less than equal to the 0.05. So we can say this n, capital N, is considered as infinite population. Okay, so we can consider them as a random sample because random sample we are taking from infinite population. Definitely, when population is finite, replacement is not done and ordering is not given importance. So we have the change the theory. So we won't discuss it and assume hypothesis is definition. Okay, so if population is finite, replacement is not done, ordering is also not given importance. So that type of concept we are not doing here. We are doing the concept for the random sample when the population is infinite and replacement is done. Okay, so the random sample and its characteristics will be denoted by capital letters as we are denoted by the x1, x2 and x3, and its corresponding value is a small letter, that is x1, x2 and so on. Okay, this is tuned with the practice of denoting random variables by capital letter and its values corresponding to the small letters. Thus, a particular sample is a value x1, x2, xn of an n-dimensional random variable. Joint we have done now. So it is an n-dimensional random variable x1, x2, xn, and equivalently point in n-dimensional space. The values are x1, x2, xn, called the observed values here of x. Correct. So it is the n-dimensional. So we are talking about the joint distribution now. So we are using here the joint distribution and the term is x1, x2, xn, n-dimensional random variable, and its values are small x1, small x2, small xn. And what is the property we are taking? IID. Okay, IIDs means identical and independent distribution. Okay, independent and identical distribution for the joint distribution that we are taking x1, x2 up to xn. So we have done a multivariate random variable today. So that part is we are doing in the statistics. Okay, so now the course name is the statistics. Statistics. Okay, so this S is there. Now the word is statistic. S is not there. So it is any quantity whose value can be calculated from the sample data. So any function of this x1, x2, xn is known as a statistic. Okay, any function of this random variable and dimensional independent and identical distributed random variables are known as statistic here. So prior to obtaining data, there is an uncertainty as to what any particular statistic will result. So therefore, a statistic is also be a random variable. Okay. So we are saying, like for example, x bar. X bar is what? X1 plus x2 plus and so on plus xn divided by n. That formula we have done now. Okay. So this is also be a statistic. Correct. When we are not fixing the value of x1, x2, xn, then it is a random variable. So that's why the statistic that x bar is also be a random variable. We have already proved it. We have visualized it in the last slides now that x bar is also be a random variable because when we are taking different samples, so x bar is coming different for each sample. Denoted by an uppercase letter, a lowercase letter is used by the represent the calculated or observed value of a statistic. So capital X bar we are using here. as a random variable, and small x bar is what? Its calculated value. So that's, we have done this slide. So x bar is equal to summation of xi divided by n. Sn square means what? The sample variance is 1 upon n minus 1 summation of xi minus x bar whole square. Okay. Some more statistic is what? Sample mean, sample minimum, minimum of all x1, x2, xn, sample maximum, that is the maximum of x1, x2, xn, then sample range, that is maximum xi minus minimum of xi, and sample variance. So do you remember the formula of variance of x? That is what? Expected value of x minus mu whole square. So that is by definition, but how we can calculate it? Expected value of x square minus expected value of x whole square, है ना? So same here, the basic definition is this one, but computational formula we are applying here, this one. Okay, that is n times of summation of xi square minus summation of xi whole square divided by n upon n into n minus 1. So this is known as a computational formula of sample variance, and the earlier formula was the definition, basic definition of the sample variance, correct? And these all are the sample variance, sample mean, sample range, and so on. This is not for the population. So I already mentioned earlier and showed you the by the example that population parameter are different than the sample parameter. So you are talking about the mean. So which mean, the sample mean or population mean? You have to be very much clarified. Okay, then we are talking about which mean, which variance, which range with maximum. Okay, that we have to mention it clearly. Now one example we are just doing here. So in a random sample of 9, actually time is almost over, so I will upload the slides up to here. This example will also be there, so you just go through this example. Any doubt, you can do it. I'm always giving you the tips for doing it. Hint and tips we can't give her, but I will say here that I already give you the practice problems. At least that practice problems you can do it. That is reduce your calculation part. I can understand your march is also going on from us, also march is also going on for us. So don't worry about it. Just try to concentrate little bit and then you can just do it. You will pass the marks. But some time, at least some time you have to spend for this course. Without spending the time, it's very difficult because it's a mathematical course. So in the examination, if you are just seeing the slides only, that's very difficult to do the question in the examination. Please do it by your own hand. So this is the main or important tip to do the any course of mathematics, that please try to do the practice, do your problems. If you're not doing 5 questions, do at least 2 questions, but your own hand, without seeing anything. Most of the students were doing what? They are just reading the slides, they are just seeing the recording only, they are not doing the practice. So at the time of examination they will confuse. So that's why I'm saying here. There are so many distribution. I told you in the discrete case, it is, you have to find out all properties I told you, but in the continuous case it is already mentioned that you have to this particular random variable follows this distribution. So there is no need to find out that okay, which formula we have to apply. Okay, there are definitely many distributions. So time is over. I will upload the slide up to here. Thank you so much. Mr. Swapnil, not till today. I already mentioned it is before the section 5.10. Okay, it's up to the exponential distribution. So we are taking the extra, this is the extra course for EC3, not for EC2. On the you can see here, I already mentioned it. Okay, so it is a very less portion. This is not covered in this one here. Thank you. Thank you so much. Have a nice day. Because you have the another class at 10:30. So I have to stop here.